Perfect. All right. So I see myself with a little bit of lag, but I hope that you don't get that lag. Anyway, all right, I'm going to start with the presentation. So first of all, I would like to thank the organizers very much for this invitation. It's a great honor to be one of the plenary speakers. Today, I'm going to talk to you about some recent work we've been doing with Antonia Schmieder from ZIP at Germany, and Felipe Serrano, who was a PhD student at ZIP and now recently started working at IDEM. And this work has been more or less, as the title suggests, introducing intersection cuts, well, not really introducing for the first time, but using intersection cuts for QCQPs with something that we call the maximal quadratic-free sets, which I'll let you know in a minute what it is. So first thing first, let me start with the mandatory intersection cut slides, which explain intersection cuts in a few pictures. That's the nice thing about intersection cut, that you can really explain things with pictures. So the idea is the following. The idea is the following. We consider some feasible set, which we only need it to be closed. We don't really need anything else from it. And then what we do assume, though, is that we have an LP relaxation of it. So let's say we're solving a QCQP. We start with some feasible, with some LP relaxation. We get a vertex solution, all right, and we want to cut that off. So what intersection cut does or proposes is to let's say try to find a convex set that contains the point that I'm trying to cut off, okay, but that it doesn't intersect my original set S. So this is why it's called S-free. The good thing is that if you're able to do this, then you can actually create a cut very easily. You just look at these rays, okay, and look at where these rays are intersecting your convex set, and then usually you assume that your relaxation you consider a simplicial conic relaxation. So you have n rays, and so you have n intersection points, and then you can construct a hyperplane going through it, and you can prove that this cut is valid. And since it's S-free, it will not cut into here. And since since the point that you're cutting off is inside the convex set, you will actually cut it off. Okay, so this is what you would like. So one important thing is that if you have a larger S-free set, in this case, for example, the purple set, and now you look at the intersection points of that set, which are these black points over here, you get a deeper intersection cut. It might not necessarily dominate strictly, but it's always, you can prove that it's always at least as good, okay? So in general, we will be interested in maximal S-free sets, which are, as the name suggests, sets that are not contained in any other S-free set. Okay, so in a sense, this is giving us the best we can hope for using this paradigm, of course. So the case that we will deal with in this talk is a quadratic set. So I'm going to assume that my set S is a single quadratic inequality. And I'm going to assume that I have a solution to an LP, which is going to be S bar, say, which is not in this set. So a few important comments regarding this. This doesn't mean that this applies to problems that only have one single quadratic. It also applies to multiple quadratics. The thing is that we're just going to construct a cut using one quadratic that is violated. Okay. And second, another important thing is that the intersection cut also uses this LP relaxation that I mentioned before, which usually carries information of all the other constraints as well. So the cut that you're constructing using this S-free set, even though you're looking only this as S, you will still be including information of the rest of the constraints, because the LP relaxation that you're using has information on the rest of the constraints. Okay. So that's the setup. Some related work, and again, I would like to apologize if I left anyone out, but the list is long, so I wanted to mention briefly a few related works. So the first four the bullet points here are intersection cuts in non-convex settings. So we're definitely not the first ones in doing so. There's some work in using intersection cuts in bi-level optimization. So you have this notion of bi-level free sets. Fischetti and Monaci use this intersection cuts looking at bilinear terms. So constructing what they call bilinear free sets. Felipe Serrano constructed concave underestimators of factorable functions. So what you get using this is, let's say, reverse convex relaxations. So you can use that as to construct as free set. And then myself with Dan Beanstalk and Chen Chen, we looked at extended formulations of polynomial optimization and constructed what we call outer product free sets for constructing intersection cuts in those settings. And beyond intersection cuts, there is also important works. Just to mention a few, some works that you could use for, let's say, deriving valid inequalities using, instead of, let's say, a simplicial cone and a quadratic, you could use, for example, a second order cone and a quadratic. Okay. So the overall goal of this talk will be to show you how we construct this maximal quadratic free sets. That's the first thing. So I'm going to show you what is the maximality criteria that we developed. So essentially how you prove that something is maximal in this setting. Then I'm going to move to show you how constructed maximal quadratic free sets for homogeneous quadratics, then non-homogeneous quadratics. And in the end, I'm going to show you some computational experiments we did with this. And this will cover two papers, one of myself and Felipe from 2020, published in IPCO, and one recent in this year's IPCO with Antonia and Felipe. Okay, so let's jump into how do we prove maximality. So let's look at the integer programming case. So in the integer programming case, there is a very a beautiful criteria for determining if something is maximal lattice-free set. So in this case, what our set, the green set, let's say, is the set that the convex set that we're constructing. The red square is what we're trying to cut off. And we want in this case, we want our set to not contain any lattice point in the interior. So this set right here is not maximal. As you can see, you can easily imagine that you can enlarge this. So if you enlarge it like this, then here you see that essentially these points here are preventing you to enlarge it more than this. So what is going on here, and what the criteria for lattice-free sets tells you, is that a set will be maximal lattice-free in this case if there is a lattice point in the interior. Well, if it's a polyhedron, one thing, and second, if there is a lattice point in the interior of each of the facets. Okay, so we wanted, inspired by this, we wanted to bring this in a setting where, well, there is no lattice, there is a closed set, but see if we could capture sort of the same type of criteria. So inspired by this, we define what we call a point exposing an inequality, okay, which is defined as follows. So we consider some inequality. We'll say that a point will expose that inequality if the inequality is, and the inequality has to be valid for the convex set. I forgot to say that. If the point is tight for that inequality, and the inequality is the only valid inequality tight at that point. So let me give you an example of this. So if I look at this point right here, where I have the mouse pointer, and I look at the purple inequality. So in C, which is the ball, that point x0 is the only tight point on this inequality. Sorry, I said it the reverse way. This inequality is the only valid inequality tight at that point. Okay, all the other valid inequalities around here or somewhere around here will not be valid at that point. Okay, so in this case, we say that this point is exposing this inequality. So the idea behind this exposing notion is to sort of capture the idea that we do need this inequality. Okay. So the criterion that we developed, the first version of the criteria that we developed, is the following. If you have a set C, a convex set, and described by a bunch of inequalities, okay, that we just denote like this. And let's say that this set C now is S-free, okay? And furthermore, suppose that for every valid inequality, there is a point that exposes that inequality, but that is in the intersection of the set and C and the convex set. If this happens, the set has to be maximal as free. Okay, so the idea is, well, if I look at this ball, for example, and I define as S everything outside the ball, and I look at all the boundary, well, I have a bunch of exposing points, right? We have a point here that is exposing this inequality, and essentially every point in the boundary is exposing one inequality, and the points in the boundary are both in S and in C. So this gives me a certificate that the set that I'm considering here, the set C, is maximal, that I cannot enlarge it further than this. Okay, and this is generalizing this sufficient part of this criterion that I mentioned before of the lattice free sets. Okay, it's not necessary, but it's sufficient. Okay, so how do we use this criterion? And I'm going to start with homogeneous quadratics, which is the easiest case. So if I consider a homogeneous quadratic that looks like this, okay, I can diagonalize that inequality, and I can assume that I will be interested in a set that looks like this, okay, which is norm, essentially norm less or equal than norm. This is how many members you have here and how many members you have here will depend on the signature of the matrix Q, okay? But it suffices to consider this set. The transformation from here to here, it's linear and invertible, so you can construct the maximal S3 set here and then go back to this set, okay? So in 3D, unfortunately, there's not too many of these. So it's either this hourglass or the complement of the hourglass, but it will be enough to illustrate the sets that we will construct. So for this set, for this homogeneous case, the norm less or equal than norm set, it's not too hard to prove that this set is SH free. And let me go back for a second. So this set, what we do is to lower bound this using a subgradient, okay, and then reverse the inequality because we want the set to be S free, okay. So we relax the set S and then we look at the complement. That's the idea behind this set. That's why now the norm appears here before it appears with a minus sign. So here appears with a plus, and less or equal than lambda transpose X, which is the inequality that you obtain from lower bounding the norm. Okay, so what we show is that if you take a particular lambda here, which is related to the LP solution, okay, this X bar comes from the LP solution, this set is S-free and contains the point that I want in the interior. So it's exactly what I want. And furthermore, using the criterion that I just showed, we can prove that this is maximal SH-free. So in this two cases, the set that we would construct would be something like this wedge in the hourglass case, or it will be one of the two second order cones essentially in here in this the complement of the hourglass. And the proof is simply looking at the valid inequalities and seeing that they have many exposed points in this case, like all this line touching there, it's exposing this inequality, and the same below. And this one is the same argument that I mentioned before for the ball. Okay, everything in the boundary essentially is an exposing point. Okay. So now let me move towards the non-homogeneous case, but before we have to take an intermediate step. So a non-homogeneous quadratic, you can always bring it to a form that something like I mentioned before, norm less or equal than norm, and then an equality. Okay. This comes from the homogenization part. But before jumping into this, I'm going to study this relaxation, which is, instead of looking at the equality equal to -1, I'm just going to look at less or equal than 0. Okay, so this is essentially like the hourglass. You can imagine the hourglass, but then you slice it and you look a half space. You slice it with a half space. Okay. And in this case, it turns out that we need to distinguish in two cases, depending on the norm of A and the norm of the relationship between the norm of A and the norm of D. I don't have too much time to explain this, so I'll be happy to explain this in the breakout room. But the construction differs on whether this is bigger or this is bigger. Okay, and for now in this talk, I'm going to show you just case 2, which is the harder case actually, but it's somehow a bit richer. So this is why I want to show you the case 2. Okay, so let me illustrate what happens in case 2. So in case 2, now you don't have the hourglass anymore, as I mentioned before. You have you slice the hourglass with a half space, and you look at just one side of that. Okay, and now the set that I had before, which was this wedge, is not maximal anymore. In general, it might not be. So the question is, can we make this set larger? So of course we can, otherwise I wouldn't be giving this talk. And the construction comes from the following. Note that if I look at this set, the hourglass sliced, okay, let's call it like this. If I fix y, this set is convex. So if I slice it in the y-axis, it's going to be a convex set. So what we did was the following. So look here at any slice. So this is fixing the y variable, okay? And now what I'm going to do is maximize in a direction given by some lambda, okay? Don't worry too much about this lambda. I'm going to maximize in this direction for a fixed y, for each fixed y. So what I'm doing is looking at the direction, let's say pointing with this arrow, and then I compute the optimal points in each one of these. This is a convex problem, so things should be okay. And then what I'm going to do with this definition is I'm going to look at everything that is beyond here. So all the x's, let's say, that go further, I'm going to define that as being part of my set. So this is the set I defined. This is, let's say, the rigorous way of defining this is all the xy's such that this quantity right here is bigger than this maximization problem that I defined before, okay? So right now, this is only a motivation. I mean, this function can be, in principle, could be anything, and it actually is anything. And I mean, it's not nice in some cases, but in this case, at least it seems to work. I do this, I define, and I get something that looks maximal. So let me give you an idea on how we develop this case. So what we proved in this case 2 is that this function, let me go back, this function right here, I maximize for each y, I maximize in a direction, okay, and I look at the value of that. It turns out that that function in this case, and it's very important that it's in this case when the norm of A is greater than D, the function is convex, differentiable, not everywhere, but everywhere that matters. And in the paper, we have the precise statement of that. I don't want to get into those details right now. And it turns out that we can compute a closed form for that function, okay? Which is not too nice, but considering that we're working with quadratics, we were happy with this expression. And again, and I want to say this many times. I know I've repeated it already, but a very important fact, and actually quite annoying for us, is that the convexity of the function that I define really depends on this norm of A being greater than the norm of D, which actually prevented us from using the usual, let's say, maximization of something is convex, like that type of characterizations. We couldn't really use it, or at least none of the ones that we know, because, let me go back, sorry again, because it really depends on how the norms of these guys are related to each other, the convexity. So we had to work harder. Okay, but things are good. In this case, we have that the function is convex, differentiable everywhere that matters. And it turns out that the set that we define, which is, again, looking at everything that is beyond that maximum, okay, it's maximal, in this case, this set S3. And the exposing points, in this case, are exactly the maximizers. Okay, so this is what we had before. Now I look in a direction, I check there, the last point I touched, essentially in that direction. I take everything beyond that, and the same maximizer that I had there will work as the exposing point of that inequality. The same thing below. Okay, so things are looking good. And now let me show you how we bring this to a non-homogeneous quadratic now. That this is the main step that we wanted to get to. So as I mentioned before, the non-convex quadratic, a non-homogeneous quadratic, you can always bring it to this form via homogenization. So a diagonalization and homogenization. So you diagonalize and you get something like this, and this part comes roughly from the homogenizing part, okay, with an equality constraint. As before, we need to distinguish two cases, and I'm going to show you what we did in case 2, because this is the case that I've been mentioning so far. So let's look at what happened with the set that we just had before. So before I show you this sliced with a half space hourglass, and we had the maximal S3 set for that set, okay, for the orange set. But now I'm considering an equality constraints. So effectively, what we're considering now is we're looking at this hyperplane, the green hyperplane, and not at the whole set. Okay, the whole set that we had before. So if we look at what's going on in this hyperplane, I get something like this, an image that looks like this. So this is my S3 set, and this is the slice of S, the orange. So as you can see, it's not maximal. I can move this. I can grow this set. But it seems that the slope of this is fine. It seems that we only need to translate this inequality, and we will be able to get the maximal S3 set. And that's exactly what we did. What we did was actually find, because I mean, doing this analytically is a bit harder, but what we did was find for each one of these sort of bad inequalities, which are the inequalities that are not really touching the set S or close enough. What we do is find a sequence of points along S, like this red dot, which is diverging, but it's sort of getting closer and closer to the inequality. And we actually included this in our criterion for maximal S3 sets, because the criterion that I had before was too strong and didn't include, wasn't able to prove something like this. So what we did was formalizing this type of sequence as a sequence which is exposing the inequality at infinity. Okay, and we added this. We refined the maximality criterion, and in this case, we're able to grow the set and make it maximal. And as you can see here, now the set that we're getting is not S3 for the set that I had before, for the orange set that I had before. It's overlapping there, but it is maximal for the slice that I care about, which is the slice, the green slice. Okay, so let me show you a bit more formally what we did. So what we did was taking this part right here is the same set that I had before, just using a linear description. Okay, taking gradients of the function. And what we did was just translate each one of these inequalities. Okay, and what we were able to find is that this translation of the inequalities has also a closed form, okay, which we were able to derive. And with this, we actually got a closed form formula for the maximal S3 set in this non-homogeneous case, okay, which is a bit uglier than before, but again, I mean, we were sort of expecting ugly expressions that look like this. Okay, so that wraps up the construction of the maximal S3 sets. I hope I was able to give you a good idea of how we constructed these things. Now let me finish very quickly with some computational implementation that we did, which also plenty of work. So this is covered in the most recent paper with Antonia and Felipe. So what we did in this paper was show exactly what is a sequence of transformations that you can use to get from a quadratic set to one of these sets that I mentioned before. So one was norm less or equal than norm, and the other one had an equality constraint in the non-homogeneous case. And the sequence is Huygens decomposition. So we did a projection that preserves maximality, a homogenization, and at the end, a linear variable map. We described everything in full detail in the paper. I don't have enough time to do that here. And the idea is that with this, we can use the construction that I just showed you for these type of set and construct explicitly an S3 set for this set, for the original quadratic that you would encounter in a formulation. And then what we showed in this paper was also how to compute the cuts, because in order to compute the cut, you need to compute this intersection points that I mentioned before. Okay. So in what we did in this paper was show exactly for each one of these rays, okay, that are emanating from your LP solution, how the equation that you need to solve in order to get this point. And we show that it's always a quadratic equation, a single variable quadratic equation for each one of these R's. So it's simple to compute, it's very efficient. And we actually provide this these coefficients explicitly. Okay, so the point being that if you encounter a quadratic and you want to construct one of these cuts that we're advertising, let's say, you wouldn't need to do all the work that I just showed you. Essentially, you would need to just plug in, like get your ray R, your solution, and then populate the expressions for B, A, B, C, D, and E, and you would get the cut coefficients. That's the point. And in the experiments, we tested this on MINLP and almost 600 instances, which we filtered by only considering the non-convex with at least one quadratic and with a primal solution just to measure gap closed. We performed root node experiments giving this cut to skip as a separator. And we also use some additional quadratic that don't appear explicitly in the problem, which are quadratics related to this usual extended formulation of QCQPs, where you create a new variable xij for the product, for the bilinear product. And so this quadratic equality is sort of implied, right? Because this is a product of four variables, and the same four variables appear here, okay? And we use this quadratics also to generate cuts, just in the lifted space. And this is actually very related, for those of you familiar with this outer product free sets that I mentioned at the beginning. This is related to those sets, and I will be happy to talk more about those in the breakout room. So just a few highlights of the results. So this is a summary of, let's say, our best setting versus default. So in the paper, we have many more settings that we tested. So this is the best, and this shows the gap closed comparison. So as you can see, overall in the root node experiments, we did quite well. In numbers, the overall average improvement of the gap close was 9%. So you have to take into account that this is a very heterogeneous family of instances. So 9%, we're actually very happy with this. And if you restrict to the affected instances, which means the instances where skip used our cuts, this is it goes up to 15%. Okay, so this was very nice. And additionally, with our cuts, skip was able to solve 27 more instances in the root node. Okay, so we were very happy with these experiments. So with this, I'm done. I would like to summarize and give you some final remarks. So in these two papers, we are giving maximal quadratic free sets, and we're giving you some closed form expressions for these maximal quadratic free sets that you could use for quick computation of cuts. The computation of cuts will, the bottleneck of them will be solving a single variable quadratic equation. These cuts, we observed that these cuts had a very good performance in root node experiments. Some extra comments on this. This transformation to bring a quadratic set to a canonical form, which is this norm less or equal than norm form. We do not know exactly, we do not fully understand how different or what's the effect of these different canonical forms, because using different sequence of transformation, you can get to different canonical forms for the same set. So actually here, what I'm showing you is for the same quadratic, using two different sequence of transformations and constructing the S3 set and then coming back, you get actually two different S3 sets. So they really depend on how you do this transformation into a canonical form. And that's something we're only considering one for now, which is the one that we published in the last paper, but we don't know how good it would be to consider others. And another important point that I want to make, that this family do not describe all maximal quadratic-free sets, and we have some evidence for other type of maximal S3 sets that with this, even with this maximality criterion, we cannot prove yet that they are maximal indeed. Okay, so with that, I will take some questions if I have time. I'm not sure if I have enough time, and if you don't know which questions to ask, I'm giving you some ideas here of cool stuff that I would love to go deeper into. Consider this as a cheat sheet or some sort.
Thanks so much, Gonzalo, for a brilliant presentation. Does anyone have shallow-ish questions? Deep questions should be saved for the breakout room. We have 2 or 3 minutes here.
Is the maximality criterion sufficient and necessary?
So I couldn't pick who was that person. So so anonymous person. I'll answer that. It's not. So it's only sufficient right now, and we're working toward necessary.
Thank you, Gonzalo. That was good.
Thank you for the question,
Andrea.
Anyone want to take number 2? All right. I think what we should do.
Question, please.
Oh, sorry.
Can I have a question for Gonzalo, please?
Absolutely.
yes.
Yes. I'm question is for question 4. If you want to include the intersection car in special branch and bound, but intersection car, as I know, it will have a very high rank. So it may induce some numerical instability. So how can you do this to include the intersection car in special branch and bound?
Exactly. That's a very sensitive point, and this is the hardest question of all. But I'll try. So exactly as you said, the problem with intersection cuts is that it's very frequent that they can be quite dense. Okay, so that induces some computational difficulty, and we've actually seen that, and it even happened when we tried to strengthen the cut, which you would think that it would make the cut better, but it turns out that it hurt our performance because the cut is so dense that in the end you pay too much of, you have an LP that is very heavy. So our idea for doing this, I mean, we tested, let's say, a naive implementation, and in some cases it helps, in some cases we hurt the solver. So we're still working on it. Our idea is to try to make this cut somehow sparser, okay? Because the problem of this that we see here is that since the cone comes from the LP tableau, we point to that, the source of the density. So what we want to do is try essentially a different LP relaxation that somehow can give us a sparser cut, for example, that only considers the variables that appear in that quadratic, and hopefully with that we'll get a better performance in a special branch and bound. But that's still work in progress. We haven't done that yet.
Thank you very much.